Alright folks, so this is going to be the first real substantive video in my series on algebraic number theory. We're going to start with the first section of Milne. So we're going to talk about, basically, the goal of this section is to give you some of the basic definitions from commutative algebra that we're going to need. Okay, so the first is the notion of an algebra over a ring. Okay, so let A be a commutative ring with unit and let's suppose that phi from A to B is a unital ring homomorphism we call the pair B bar phi and A algebra. Okay. So this map var phi essentially allows us to multiply elements of A, or multiply elements of B by elements of A. So what do I mean by this? So example, okay, let's consider the inclusion. So maybe one of the simplest possible examples, we can include Z into Q just by sending 1 to 1. Okay, and the pair, okay, or the pair Q comma iota is a C algebra. Okay. You could also, I mean, this map doesn't have to be injective. You could also consider the projection pi from Z to Z mod P, or really Z mod NZ for any integer n. Okay. Then Z mod NZ pi is another Z algebra. Okay. This essentially this ring homomorphism var phi allows you to multiply elements of B by elements of A via their image under var phi. Okay. Okay. So a couple remarks I want to make. So I guess the first thing I want to say is that every ring for the context of this lecture series will be commutative with unit. So every ring, unless otherwise stated, is commutative with unit. Okay, and I guess I should also say every ring homomorphism is unital. Okay. We also will often omit the map So if B var phi is an A algebra, we often just refer to it as B, where the map var phi is implicit. Okay. Okay. So some important definitions when it comes to ring algebras, algebras over rings. So let A and B be rings, and A subset of B a unital subring. For beta 1 through beta m elements of B, we can define the A subalgebra of B generated by beta 1 through beta m we denote this by A adjoin beta 1 through beta m to be the smallest subring of B containing A and beta 1 through beta m. Concretely, so this is kind of like an abstract definition of what this thing is. Concretely, it's really just polynomials in the beta sub I with coefficients in A. Okay. So Milne goes on to define ideals in rings, the sums of ideals. Okay, these are hopefully things that should be familiar from ring theory. He defines a quotient ring, which I've already kind of talked about up here. There's an important proposition from ring theory which I want to remind you of. Okay, that has to do with quotient rings and ideals in quotient rings. Okay. The proposition says, let A be a ring and mathfrak A an ideal in A let pi, this is going to denote the canonical projection from A to A mod this ideal. And essentially, this map pi is going to induce a bijection between two different sets of ideals, one in A and one in the quotient. So we're going to let S1, this is going to be the set of ideals. Set of ideals in A such that B is an ideal containing our quotient ideal A. And S2, this is going to be the set of ideals, just the set of ideals in the quotient. Okay. B is an ideal. Okay. And it turns out that there's a bijection between these two things. Define pi star from S2 to S1 by pi star of an ideal is the preimage of that ideal under pi. Then pi star is a well-defined bijection. So if you're being careful, you should check that pi inverse of an ideal is again an ideal. That's really what I mean when I say well-defined here. And the bijection property, I mean, hopefully at this point we know what bijections are. So I'm not going to prove this proposition. This is really just an exercise in ring theory, and is more here as a reminder rather than an important result. There's something else I should say here. Furthermore, just to add on some information. Furthermore, pi star induces a bijection between both maximal. Okay, maybe I'll be more clear what I mean by this. So this map pi star, if I restrict to the maximal or prime ideals, it also remains a bijection in the following sense. So between maximal slash prime ideals of A mod A and the maximal slash prime ideals of A containing A. Okay, so this is, I think, maybe I've heard this referred to as like the fourth isomorphism theorem or something like this, but it's a fairly meat and potatoes result from a first course in ring theory. Okay, and the last proposition from this section, which is important, which is another, I think it's even like the third isomorphism theorem or something like this. Another important result from ring theory. Let A be a ring and A subset of A an ideal. Then for B contained in the quotient an ideal. And pi, again, this is going to denote the canonical projection. we get an isomorphism of rings. Bar phi from A. So if I take the preimage of this ideal B in A and I quotient by A, this is the same thing as if I took my quotient and then I quotient it again. Okay, and the map, I'll even tell you what the map is. And it's kind of like the only thing you could think to write down. Defined by phi of A plus pi inverse of B equals A plus A all plus B. Okay. So this map is a bijection. It's a ring homomorphism. It's well defined. Things like this. Again, another meat and potatoes result from commutative algebra. Okay, so these are the results I want to highlight from this first section on Milne. As we get into the more like as we get into things that aren't just prerequisite knowledge, I'll start being more careful about proving things. But right now, this is mostly just serving as a reminder and kind of giving you a base of knowledge that I'm going to assume going forward for the rest of this algebraic number theory.